Yes, I'm happy to introduce our second speaker. So I'm happy to have Irina Wang here. She's from a PhD candidate at the Princeton University. She has done research already on decision-focused learning, and especially robust optimization, optimization-based control, and is also interested in stochastic multi-level problems. And I was very impressed that she already won several awards very early in her career. So, for example, the Princeton Wallace Memorial Fellowship, the Informs Computing Society Student Paper Award, and the Princeton School of Engineering and Applied Science Excellence Award. So I'm very happy to have you here, Irina, and please.
Thank you, Hannes, for the introduction. And I'm very honored to be invited to talk in this webinar because I have actually been paying attention to this webinar in the previous years and I've attended several of the talks. So yeah, again, very honored to be invited to speak. So today I'm going to talk on my work on fast online distributionally robust optimization via data compression. So this is joint work with a collaborator, Martha, who has recently graduated from ETH Zurich, and my advisor, Bartolomeo Stellato. So the setting that wait, considering is also this decision-making framework with uncertain parameters, very similar, I think, to Justin's framework, where we're considering this objective function f, where we have optimization variable z, the uncertain parameter u. So the notation is slightly different from Justin's, but the overall idea is the same. And I consider this objective function that's maximum concave in the uncertainty. And I would also have additional constraints, Z lying in the set calligraphic Z, which could encode deterministic constraints that could also include mixed integer constraints. All right, so with this setting, how do we actually deal with the uncertain parameters? Well, a view for stochastic optimization is that you can assume full knowledge of the underlying distribution and solve the stochastic optimization problem where you're minimizing with respect to the expected value of the true distribution. But obviously, this is not really realistic, right, because we can't really assume to know full knowledge. What I'm considering is actually this framework where we acquire new information over time, where we have this timeline. At time t, we compute our decision based on the information available. At the same time step, we collect some sort of new information on the underlying uncertainty, and we make a new decision based on this newly acquired information. So then at each time step, how do we make this decision? So the robust optimization framework is, we define some uncertainty set U of t and solve this optimization problem where for each realization with this uncertainty set, we ensure this constraint violation and constraint satisfaction, of course. And then here I put this as a f-graph form. So I have minimizing h, the objective value now, subject to this uncertain constraint. And the important part here is how do we build and update this uncertainty set? Because the uncertainty set is completely related to how well our final solution is, right? If we have a really large uncertainty set, then yes, we could cover all of the possible uncertainty that we get that's out of sample, but at the same time, it could be so large that the solution that we get is suboptimal, so we are overly conservative. Whereas if we have a small uncertainty set, then we might have a really good in-sample solution, but out of sample, we perform not really well. So traditionally, there are several ways to build the uncertainty set. We could assume that the decision maker has no distributional knowledge about the underlying uncertainty and only know its support. Or we can assume that we know something about the distribution and that it lies in an ambiguity set of possible distributions, such as they could share certain moment information, but the actual distribution is unknown. And these frameworks could be pessimistic. I mean, it could be conservative in that they could rely on some pessimistic assumptions of the uncertainty. So we get suboptimal solutions. And in recent years, there's been a large drive in data-driven optimization, where we instead use a given data set, right, collected data, to better inform us on this uncertainty set or this ambiguity set. We could use tools like hypothesis testing or quantile estimation or deep learning to build a more high probability region of the underlying uncertainty, and then use this better, high probability region instead of the, just support information and arrive at better solutions. Similarly, there's been a drive in the data-driven distributionally robust optimization where we closely use the collected data to form our ambiguity set, and that's going to be more of the focus today. So this data-driven DRO framework is as follows. At some time t, we have a total number of data points n of t, and we can build the empirical distribution around of this given data set. And the ambiguity set will be constructed as a ball around this empirical distribution. So we have some parameter p here that's kind of the order or tells us the structure of this ball, and we also have an epsilon parameter that's the radius of the ball. So, for example, a very popular way to characterize this ball is to use this Wasserstein distance. So, in this ball, we include all distributions q that's within this Wasserstein p distance from this empirical distribution, and we use this radius epsilon. Right, and for those of you who might be unfamiliar, the Wasserstein distance is the optimal transport distance where we're kind of characterizing the amount of probability mass we have to move to transform one distribution into another distribution. Right. So with this type of ambiguity set, we're solving then the DRO problem where instead of requiring all realizations within the uncertainty set to hold for the uncertain constraints, we have that with respect to the worst case distribution Q in this ambiguity set, that this expectation, we're minimizing, this expectation. All right. For the DRO framework, what we want is, in the end, to satisfy these probabilistic guarantees, right? And that we want, with respect to our solution z of t and h of t, so zt is again our optimization decision variable, and ht is the kind of the epigraph, the value of our optimal solution, the value of our the problem. And so what this encodes is that we want the in-sample value to upper bound the out-of-sample expectation with respect to our solution z. And this expectation form is powerful because it can actually imply risk metrics. For example, if we take f to be of a certain maximum affine form, then we could model things like the conditional value at risk, which could turn this expectation form constraint into something like a chance constraint. So it's pretty powerful in its modeling powers. But the problem here is that we don't know the true distribution p, right? So what we do have, however, is the data set. And we also know that our data-driven solution, right, z of t and h of t, is this random variable that depends on the straw data that we got in the beginning. So what we can have is the finite sample data-driven probabilistic guarantee, where for this data-driven solution that we get, with respect to the product distribution of the data set, that this expectation constraint holds with some confidence parameter or probability of constraint satisfaction. And herein, though, lies this trade-off between statistics and efficiency, because when we choose this the radius of this Wasserstein ball, we have to choose it in order to guarantee the finite sample guarantees we had before. It would scale with the number of data points we have, and m here is the dimension of the uncertain parameter u. Right, so if the dimension of u is really large, then this decay of the radius when we have more data is very, very slow. So the trade-off lies in here, right? When we have more data n, it means that we have an empirical distribution that's a much better approximation of the true distribution. But at the same time, when we formulate the distributionally robust optimization problem, it actually ends up having a lot more constraints. So I'll show in a later slide how that works. So the problem is this, right? We want to, in the setting where we're getting new data over time, we want to continuously reformulate and resolve this problem. When we have new realization of the data, right, we add this additional constraints to this problem. And when we have this mixed integer formulation, right, the additional of adding these constraints and reformulating the problem itself could take a lot of time, and not to mention solving this problem. And we know that while we can reduce this radius, when we have new data points, right, according to the rate of decay above, right, this decay of the radius is not enough to offset the increase in the computational effort of increasing the number of data points. And even actually, if the radius is taken to be 0 and we're just doing sample average approximation or empirical risk minimization, where you're just using the data points as is, right, even with a lot of data points and for mixed integer problems, this could also be very expensive, right? So this is even without considering the DRO framework. Right, so there actually has been some works that tries to break this the curse of dimensionality, in that if we choose the Wasserstein distance to be of order p equals to 1 or p equals to 2, then we can actually somehow leverage the structure of the objective function and choose a radius that scales better with n. So it no longer scales with the dimension of the uncertain parameter u, but at the same time, right, we have these modified finite sample guarantees where we introduce this trade-off term to counter the effects of having the smaller radius. So basically, in this work by Gao and Clewait, they choose the smaller, so in exchange for a smaller radius, that they can use in solving this robust this Wasserstein DRO problem that kind of reduces a little bit of the computational complexity, right? We introduce a trade-off. But this does not solve the problem of introducing computational complexity by having a lot of data points, right? The N of T does not change. So what we have is that this idea where we want to introduce another trade-off for faster computations by reducing the number of data points that we're using in this distributionally robust optimization framework. And of course, we would also add, a different term that's not this rho term here. So this brings us to the idea of data compression for decision making under uncertainty, where this idea is actually not exactly new. There's a long line of work in scenario reduction, where given a set of scenarios, we're given a distribution, we can use whatever method you want to find this smaller set of representative scenarios to solve your stochastic optimization problem with, and to find the smaller smaller set of scenarios, there are many ways. There's like ways you can do clustering, you do Wasserstein distance-based clustering, or also defining the scenarios based on the actual optimization problem you want to solve itself. And of course, this line of work also lies the history of information theory, compressed sensing, and quantization idea. So it comes from a long history. So data compression is something that people have looked at a lot, and our method builds off of these data compression approaches, like scenario reduction, where we're kind of agnostic to the method by which we use to find the smaller distribution, and we instead focus on building trade-offs of solving the Wasserstein DRO problem with a larger set and with a smaller set. So the main idea is to reduce the data granularity and the computational time by using these scenario reduction techniques. So for this part of the talk, we want to consider just a fixed time set T. And at the fixed time set T, we have access to the set of data points which we can create into clusters. And again, we can use whatever clustering method you want to get to these clusters, k-medians, k-means, Wasserstein-based clustering, or other interpretive clustering methods. So whatever method you use, we get through this clustering algorithm where we have the k as the number of clusters, ck as the cluster assignment. And once we get there, we use the cluster centers instead of the original data in our Wasserstein DRO framework. So overall, at high level, this compressed DRO framework is like this. We have the data set. We use your machine learning clustering algorithm to output the cluster weights, which is the proportion of data points in each of the clusters. And the cluster centers of d bar of k, which is the mean of the data points in the cluster. And we can use this to build this reduced ambiguity set, right? Because the cluster weights and the cluster means essentially gives us this reduced or compressed empirical distribution of the data. So we call that p hat of k. And we built this ambiguity set as the ball now around p hat of k instead of the original p hat. Right, and then with this ambiguity set, we solve this reduced or compressed DRO problem where we're finding the worst case distribution with respect to this ambiguity set p of k. And we know that this work that I referred to, which is the previous work of mine, we view this actually in the robust optimization framework. But in this work, for simplicity, we look at it directly in the DRO lens. Essentially, the way that we solve this problem is the same. So how do we solve this problem? So we assume that the objective function is a maximum of concave formulation in terms of U. So we can use standard arguments in Lagrangian duality to create this reformulated way of this to solve this problem. And we note that the epsilon value for the radius of the uncertainty set, the weights, parameters W, and the centers, d bar, are all within this formulation. And also another important thing to see is that at least one constraint is required for each data point and each function piece that we have. Right, so for each k and for each function piece, we're introducing essentially new constraints and also new auxiliary variables. So like the v's and I think the y's are all auxiliary variables that we have to add in this reformulation, and it becomes very expensive if we have a lot of data points. And another thing that we want to note is that when k is constant, actually the structure of this problem doesn't change, right? We could have just the epsilons, the w's, and the d bars as parameters of the problem. And when we want to resolve it with new values of parameters, we can just replace these values without changing the overall structure of the problem. Whereas if we're in the original DRO framework and we're adding new data points, then we actually have to add new constraints, and actually the entire structure of the problem changes, and the compilation would be more difficult. All right, so this shows us the computational efficiency, or like the reduction when we have less the data points that we use. And now we want to compare its performance. So we want to compare the performance of this nominal DRO and our compressed DRO. So we have the assumptions that the objective function is going to be either L smooth or M Lipschitz in the uncertain parameter U. And with this assumption, then we can build this performance bound between the nominal in-sample solution H of t and our compressed in-sample solution H of k. Right, so we show that in one direction of the bound, so this is ht minus hk, it's going to be the minimum of some dual related distance. So this dual related distance, I won't go into the details of it, but it involves the dual variables or the auxiliary variables of the reformulated problem that I showed in the previous slide. And it could also depend on the Wasserstein-1 distance between the empirical distribution and the compressed empirical distribution, as well as the radius epsilon of the uncertainty set and the Lipschitz constant of the functions. And on the other hand, on the other side of the bound, so this is hk minus ht, it's similarly bounded by certain distances that's related to the clustering. So it could be the squared Euclidean clustering distance as opposed to the Wasserstein-1 distance in the left-hand side bound. And the right-hand side, you could also have a upper bound that's like the Wasserstein-1 distance. So, and also we have a delta term that scales with the epsilon radius of the uncertainty set. So, and this comes from the mean robust optimization work that we had before, and also as well as results from Kantorovich-Rubinson duality. And the main takeaway here is that we want to choose the best or the applicable bound to our problem. All right. So with this type of result, we can then get finite sample guarantees for our compressed framework. So we can upper bound the outer sample value that we get for our compressed DRO problem. So we have the outer sample value, which is the expectation with respect to the true distribution of our solution Z K. And this is going to be upper bounded by the in-sample certificate, which is the in-sample value HK plus one of the bounds 5 underscore K. And this is in turn upper bounded by the nominal in-sample value ht plus this trade-off term, which is the summation of the two phi terms. So if you think back to what I had previously in terms of when there's a result in the breaking the curse of dimensionality, this is a very similar flavor of finite sample guarantee, where we're adding some trade-off term in addition to the nominal solution ht. To trade off for now the reduced computational effort of having less data points. Okay, so what we see is that when we have a better clustering algorithm, then we have lower trade-offs, right? Because the phi terms here are dependent on the clustering discrepancy between the distributions. And of course, it depends on the value of k. When we have more clusters k, it means that this clustering value is going to be naturally smaller. But of course, that means that we have a higher computational requirements. So the trade-off lies in finding the value of k that's both small enough so that we have low computational efforts required, but also a relatively good clustering algorithm to have a lower discrepancy here. All right, so that was bounding the difference in the static framework where we're fixing the single time set. So now let's look back to the online framework where we're making the decision in sequence, right? After we get new realization of the uncertainty, right? So we want to update the ambiguity set after we get each realization of uncertainty. So we think instead of the fixed clustering algorithm, we have this adaptive clustering algorithm that we want to keep consistent over time. So we can use many different algorithms. So if we have a finite support, then we can just partition the support and have the clustering be assigned based on this partitioning. Or we can do k-means reclustering at each time t, which requires keeping all the data points that we have in the memory. Or we can use other state-of-the-art machine learning clustering algorithms where we have things like microclusters and macroclusters that reduces the memory requirement. And then, after updating the ambiguity set based on whatever clustering algorithm we used, we compute the new decision where we, update the weights and the means of the cluster means. Okay, and again, I want to say that this is just some samples of the clustering algorithms that you would use with different, time in the initialization, time in the online part, as well as the memory requirements. So you would want to use whatever clustering algorithm that best fits your data and best fits your, memory or time requirements. And we want, and if these clustering algorithm or it has the supports that satisfy certain requirements, such as being pairwise disjoint, having non-zero measure, being the border itself having zero measure, and we have to fix the support after a finite time step tau, then we can show that the clustering arrangement or the cluster compressed empirical distribution converges to this distribution pk star. And with this, we can then have some online dynamic regrets analysis. So dynamic regrets is that we want to robustify our solution with respect to the subsequent realization of the uncertainty. So we're defining the regrets as this formulation where we're comparing our performance on the left-hand side with respect to the nominal performance with respect to an oracle that knows information from one step ahead. So essentially, our solution ZK is going to be computed with respect to the ambiguity set PK at time t, and then we're finding then the mask. We're then finding the uncertainty U with respect to the ambiguity set that includes the subsequent realization of the uncertainty, and of course includes all the data points. So this is not PK, this is P. So on the right-hand side, we essentially have the nominal performance of the best nominal performance that has access to all the data, and we're comparing our performance, our online performance to that. So we want to evaluate this average performance gap with respect to the oracle, and we can show that when the time is going to be much higher than the tau time step where we fixed our cluster support, then with some probability, right, we show that this regret is bounded by these two terms, right? There's like time discrepancy term that kind of characterizes the discrepancy we have of having the one-step information loss, or like we don't know the oracle of the future time step, and then we also have this clustering discrepancy that cannot be reduced over time because it depends on how well we chose our clustering algorithm and how good the final converged clustered empirical distribution we have. Right. So when the time steps goes to infinity, then we can show that the time discrepancy disappears, and we essentially have this converged trade-off between the nominal DRO and our compressed DRO. And we can also view this bound as the asymptotic performance bound. So essentially, the right-hand side is kind of the converged trade-off term that we add to the nominal stochastic optimization solution. So this is the trade-off that we incur for clustering when we have infinite amounts of data. And we also show that when k goes to infinity, of course, then we recover the nominal results where this regret goes to 0. Right. So lastly, I wanted to look at the example, which is a sparse portfolio optimization problem, where we're minimizing the conditional value at risk of our portfolio. So the conditional value at risk on the right-hand side here, I have an image, is kind of the expected value of the tail of this distribution. And so here, this is the portfolio, I think the portfolio losses that we're bounding the C-bar of. And we're here choosing this portfolio of a certain number of stocks. So it's bounded by gamma. And we have the setting where we consider the data, stock data, from 5 years of S&P 500 data. So we get this data online, and then we fit a distribution to this data, and we generate synthetic data from this fitted distribution. And we consider the setting where we're looking at the C-bar with 0.2 risk. We have M equals to 50 total stocks that we're considering. Gamma is equal to 8. So we're considering this really small framework here because we want to compare to Wasserstein DRO, which is very, very expensive even for this small framework. So we show the computational speedups for this problem where we choose K, the number of clusters, to be 25, and we're looking at a horizon of 2,000 time steps. So we're over 2,000 time steps, we're getting new information at each time step. And we show that, yes, on the left-hand side, we have an in-sample certificate. So our solutions, our methods is the red and the blue methods. So we use two types of clustering methods. One is the online two-stage clustering that has lower memory requirements, and a reclustering method, which is just k-means reclustering. And we show that for both of these methods, we of course have according to our theory, we have a larger certificate compared to Wasserstein DRO and sample average approximation. But we have higher confidence that our certificate upper bounds the outer sample value. And in terms of computational time, as the time goes on, we see that we get multiple orders of magnitude speedups compared to Wasserstein and DRO, as well as compared to sample average approximation, where we actually didn't even account for the perturbations around the data points, right? We're just using the data points exactly in this empirical risk minimization approach, right? So we're even outperforming that in terms of computational time because we're keeping our formulation, as I showed before, as a fixed small problem. And we show that out of sample, we're also very similar in performance to DRO and sample average approximation. And we know that in theory, like sample average approximation, when we have more data points, right, it essentially, we are essentially approaching the true data points, so the true distribution. And so it has really low out of sample error. And we're showing that our method, which is, has multiple orders of speed up, can also achieve near optimal auto-sample values. All right, so overall, we have an approach that works with arbitrary online clustering methods as long as it satisfies certain regularity constraints. We theoretically analyze the effects of clustering on the solution quality, on the finite sample and asymptotic performance guarantees. We provide this regret analysis with respect to a one set of head oracle, and we show that we obtain multiple orders of magnitude speedups compared to sample average approximation and wash time DRL. So yeah, that concludes my talk. So please let me know if you have any questions.